Okay. I will be attempting to explain the LeetCode find all anagrams in a string, right? So the description is given two strings, S and P. So we're given two strings. Return an array of all the start indices of P's anagram in S. An anagram is a word or phrase formed by rearranging the letters. So, for example, ABC would give us CAB, would give us IACB, and each one of those is an anagram, right? So we need to find all the indices of P's anagram in S. So P is the shorter, I guess, string, and we need to find all the anagrams of this, all the different variations that we can get by rearranging these letters inside of S, right? You may return the answer in any order. So you're only returning the indices. So the start of the indices, the anagrams. So for example, we have ABC. ABC can be rearranged in CBA, BAC. In this case, if we go here, CBA is an anagram, right, of ABC. So we took the index 0, which is the start of the anagram. We can keep going, BAE, AEB, EBA, BAB, ABA, and then we find BAC. This is also an anagram of ABC, right? So we took 0, 1, 2, 3, 4, 5, 6. So this is index 6. So we, I guess, recorded the index 6 in our results array. And this is what we return. So the explanation, they said the substring with the start index 0 is CBA, which is an anagram of ABC, and the index 6 would BAC, which is an anagram of ABC. We have another example, ABAB, and our P string is AB, right? So we can start from the beginning. AB is an anagram of AB. BA is also an anagram of BA. AB. So we have three indexes, A, B, and A. The explanation again is the same. Is there any issues with this question?
Unless mentioned, there was there like possibly there could be redundancy in some letters, right?
Elaborate.
Yeah, I mean we could have ABVC possible, right? Or not?
We can have multiples of the same letter, but the anagram should also have multiples of the same letter.
Yes, yes.
So, for example, ABCC, it would be like this, the two C's should also be included in the anagram. If they don't, then
Yeah,
it's not an anagram.
yeah.
So, the count of each letter should be the same, no matter the word or
Okay.
the position of the letters.
Yes.
All right. So, let's take
But just
this.
before you start, I'm a newcomer here, so you just tell me the rules. It's like interruptions. I came up with a solution.
Oh,
Like all of
yes,
these
of
things.
course.
How do you manage
Yes.
it?
After I explain the problem, I ask if anybody has any idea of how to solve this, and that's when you chime in. If you have an idea, you
Okay.
can explain it. We can explore it.
Explore. Yeah. Okay. So you just like all sharing the ideas, not everybody just getting it by his own and giving up a final solution, right?
Yeah, yeah, of course. If anybody has any idea on how to solve this, they can just open their mic and share.
Yes. Okay.
So, does anybody have any idea on how to solve this?
Yeah, I think so.
All right.
But again, this is could be a pseudocode. Nothing. No thoughts about efficiency. So I thought of something like we make an array or the best data structure for this of distinct letters of the P, and then we keep iterating. Oh, that would be much. We keep iterating for each index. For sorry, C, B, A, E, whatever. Whenever we reach something within whenever we reach something within the P, we exclude it from the array, and we keep moving until we reach to it. Like we keep moving, iterating to the next one. If it's inside the P, one of the letters in P, we exclude it from the array of like the separate letters. And then if not, okay, we start over from the next index, start like get back the arrays, something like that. This is like a starting point.
So you're saying that we should keep an array with what? What does
So
the array hold?
yeah, array of like A, and array have A, B, C, like all the elements of P.
Uh-huh.
You get it? And we keep iterating like from iterating on S. So see if it's one of the if it does exist in the array that we have. Okay, now we have one element. Good. We keep continuing from the next one until, for example, here B. We exclude B from the array that we've just saved, like that have A and B and C. A. We find A. Okay, good. So A. So we had only one element left. A. Now we exclude A. We have zero elements of the array. We solved it, and then we keep moving again, starting from E and do the same thing back to the beginning. If B, for example, wasn't one of the things that we were searching for, then we get C back because we excluded it, and like we start as if B is the start of the search, or A in this case. Make sense?
We can try it. All right. So you said the array would have something like this, right?
Yeah.
Uh-huh. And then we loop through S
Yes.
and I guess remove elements from the array, right? So we
Yeah.
decided on I guess both Lo A and Menna had ideas. If you would mind repeating them.
No, I said
Okay.
mine. You say yours.
I didn't hear
Okay.
yours,
Okay.
Menna.
That's a good thing. Consider yourself
Okay.
lucky.
Look, we have it's called anagram. It's a new word for me. Okay. So the whole idea is we will, with the search, the P, we will make an array of what we are, the elements that we are searching for. Being redundant or not, no problem. We just put them A, B, C. So we put an array of A and like separate elements A and B and C. This is the search elements that we're searching for, and then we loop character by character and search and in S for each character. If we encounter one of the elements that we're searching for, okay, good, we start from there, save this in a placeholder, and then keep moving to doing and of course before we keep moving, we exclude this character from the search, from this temporary like array of elements that we have, which indicates that okay, we still searching for others. We keep doing this until we take I mean until we the search array, which means okay, now we like the array is empty. Good, we had a sequence of all of the elements that we're having. That's good. While we're doing this, whenever we encounter something that is not in the search array and in the elements that we're searching for, we start over, restore the array with all of the elements that we're searching for, and start if this is the first thing, we save this index being 2 whatever, and then we keep repeating until we reach. And of course we need to an edge case, which is we try to no, it's not edge case, forget about it. So, do you get my idea?
I do actually.
And maybe like we have the lens. We need to look for the B. So we already have the lens. So maybe create another function, small function, with which loops through the like it takes the next like semi array is of the next the length of B. So it has B is, let's say, B is 3. It takes the next the 3 indexes and sends them the function, check it, and return maybe return true or false. And based on the return of it, we will maybe add the index to the output result or not. What do you think, Sabah?
I actually, yes, I agree with you. That is a very good idea. Almost like you take each window, right? You send it to your function and you check whether that is an anagram of your like P string. Is that your idea?
Yes.
Okay.
I took
Really?
Luai idea and made it look smart. Thank you, Luai. Because mine was not smart at first.
Okay. Okay. So almost sounds like a slide-in window thing.
Yes.
So we keep
Okay, good one. Yeah.
looping through, right? And then
Yeah.
I guess each string gets compared with P, right? I am now
Yeah.
going to, let's keep this here, going to say that we
Holy
might
moly.
have different ways to check for the anagram, right? So say that we have, let's see, right? And we have our function, right? Our helper.
Hey, can you hear me?
I can, yes.
Yes, we can.
Yeah, because the last solution is if we have only one anagram, it's like for one word, and we need to check it in that string. But we have not one anagram, but a lot. So I
Yes.
think if we find those anagrams, put them in an array, and loop uh, for put them in an array, then loop through them, check if like first one if it exists in that is, if it exists, return its index.
Okay. All right. How about this? If, for example, P is very long, say like our two strings are very long, you would need a function that first generates all possible anagrams. Is that the idea, right?
Yeah,
To
we can.
generate
And then,
first the anagram and then look for them. So that's another, I believe it might take too long. And I believe
We think so.
this is very time sensitive or time constrictive.
I think so.
but if we but anyway you will do that anyway because
Not really.
you don't,
I believe the
no you don't.
generation of the actual anagrams would take too long.
No, let's hear me
It's
out.
pretty much the
That
same because if
if we have one anagram, that's your solution is good. But you don't have only one anagram. You will loop through. It's not just ABC. You will have CBE. You will have BCE. So you need to check all of them. So
Yeah.
it's one way or another.
I think my solution will solve this because you will exclude an element whenever but when you exclude you have to loop. But okay, you could in the best or in the average case or in the best case you could exclude like go exponentially. But I think my solution will solve this problem because again with each time you iterate you exclude an element. So you
Correct.
decrease the search thing, and also my solution does not depend on order. So whatever the
I don't
different
think we
anagram.
will depend on order if we use the hash map. So it doesn't matter the order if we use the
Finally,
hash map
Mina.
and
Finally,
checked like inside the hash. If it's inside the hash, we're done.
I
So
was
it
getting
doesn't matter. But
disappointed.
we will
I
start
was
as the element is inside the hash, and we're not looking. We're looking to know if it's an anagram or not. And once we get if it's an anagram or not, it will return a true or false. Once we have this return, we will add it the index we are stopping at to the result array.
I was
And
getting
we will keep looping, and we will keep looping.
yes, yes. I was getting disappointed that nobody has mentioned hash
Oh
maps
come
yet.
on! I
I
just
was just
wanted
gonna say
you to
that.
look smart. I
No,
had
so
it for a
yes.
while now.
So yes, one of the ways to actually check for anagrams is a hash map. No need to individually check if the letter in the string exists in our P string, because that is going to be expensive, right? You check if it's A, you check if it's B, check if it's C. Instead, you can just create a hash map of your window and compare it. It's going to be a dictionary, right? And you compare it with whatever the hash map of the string you have of
You
P.
mean a hash table? Is that what you
Hash
mean by hash
table,
map?
hash map, yes, yes.
Oh,
I'm
this
not
is
sure
okay.
the
I was like, I'm thinking, what is a hash table? What is hash map? Okay.
what's the difference even. Hash map.
No, I just learned it with a different one, but okay, I'm a beginner here, but that's cool.
Okay.
That's cool.
It's different, but it's in the difference is another language in Java.
Yeah, I guess. So hash tables, right?
Thank
Yeah,
God we learned C, so it doesn't matter.
yeah. I learned. Yeah,
Okay, so we really don't need this helper, to be honest. We can just put everything inside of this since function calls are expensive. So find a way to check for anagrams. I'm just gonna say now that we have at least three, right? If we do end up finding another way, we can add it. But for now, let's talk about three. So we said hash maps, right? Let's put this here. So here's the thing. We want to use a hash map to compare, or hash table, to compare this string with whatever window we have. So we make a hash table of this, and we make a hash table of this, and compare them. And if they are equal, then you add the index that you're at. If it's not, then you just move the window forward and you do the same thing. Now, it is wasteful to create like a hash table for each window, since we're only changing two characters, right? If you start from the beginning, you make this hash table, right? But to move forward, you just include a letter and exclude a letter. And that's what you keep doing for the rest of the string. You add a letter and you remove a letter. So instead of making, for example, if our string is this long, you're not gonna keep making the same hash table. And I've seen some of their tests. The P and the S are very long. So you do not keep making the same hash table every time. You just add the next character and remove the last character. And you keep going until the end of your window is at the end of the string. Does it make sense?
yeah. Can you remind me specifically with hash tables? I kind of remember but forget at the same time. But
Oh,
just
okay,
to
but
imagine this expansion and shrinking that you're talking about. You're
all
expanding
right.
for one character and shrinking. So
So
just
let's
remind
do
me.
this. Let's do this.
Yeah.
So we have this, for
Hash.
example, say that this is only gonna have our three letters, right? We
Yeah.
have A, and we have a B, and we have a C, right?
Yes.
So this hash is gonna have, for example, A1, and here, oh, okay, this is 1, this is 1, this keeps happening, okay, 1, and then 1, right? So this is our
Come
hash table. For this window, right, to add a letter, right, you just add an extra here. You add like this, and you add an E, and you add a 1, right? And then you remove C, so you delete C from the hash map, so this is gonna be 0. And that's what you do, keep going. In this case, you added B, so B equals 2, and then you remove a B, so B is back to being 1. Again, you add an A, you remove an A, until you keep going. And each time you do that operation, you check it with your P. Is this hash table equals to, let's try to because this is the hash table for our P, right? This is P's hash table. So every time you change anything in the S hash table or the Windows hash table, you compare it with P. Are they equal? If yes, then you record the index where your window starts, right? So you
I'm sorry.
add,
Can you tell me where did you get one? Is it how many times it's mentioned?
yes, yeah, that is a hash
Oh,
table, is the number of occurrences of each character in your iterable, whatever it is, like a string, an array, etc. So it's how
okay.
many times a character was, like the count of the character, being the character being the key, and the value being the count. Make sense?
Oh yeah, yeah, yeah. I had another idea of hash tables. Like I thought of hash tables, this data structure that you have an array, you have a hash function, you have an array, and each arrays could be like linked to just a single element or a linked list of elements, and you have like, oh no, no, okay, fine, fine, fine. So here the hash is just the number of occurrences.
Dictionary.
Could be
It's
something
just,
else.
yeah, it's just a dictionary. It's gonna be something like this. Um, for example, hash equal, and then it's gonna be A, 1, B, 1,
Ah,
If
C.
you're doing Sabah, can you
Yes.
do a hash of the whole S so he will understand better? Like the hash for S is
So
it will have 2
1, 2.
C. Yeah, C will have 2, and D will be 1, B will be 3, A will be 2, 3.
Okay. Finally, I got it. Finally, I got it. I'm sorry, guys. Look. I'm not really good at JavaScript. Still learning, like starting from yesterday or
No,
something. Like C and
JavaScript.
Python, really
We're
good.
not doing JavaScript. This is Python. We will work with Python.
Yeah, yeah. It's just
So
Python.
we say this is a dictionary, not a hash table in Python. So I just got confused. Excuse me,
Okay.
please.
All right. We can just call them dictionaries. We don't have to.
Yeah, I get it now. Absolutely. This is so brilliant.
Well, I call it, my nickname for it is just hash.
Yeah.
Whatever you call it, as long as it works.
Oh, now I understand why. Because I look, I told you I thought of hash table as that data structure, other data structure I know. I didn't think of it as this dictionary or hash or whatever you call it that I see in front of my eyes now. I'm sorry.
All right. That's okay. We learn. So this is
So,
the
guys, we're
dictionary.
all learning here. We're all trying to
Of
understand
course.
DSA, which is a lovely thing.
Okay.
All right. So this is the hash for the entire string. But since we're going window by window, like almost like a snippet by snippet of the entire thing, then we're just gonna have or be
Brilliant.
concerned. Yes?
No, I'm saying brilliant.
All right. So we're just concerned with the 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 occurrence of each letter in this specific window and not the rest, right? So as I said, you add, instead of making a hash table for each window, you just modify the last hash table by adding the next character and removing the previous character. All right?
Till you have like two identical hash, that's when you find where you are in the in the loop, and just like add it to the result. Am I correct in understanding, Sabah?
Exactly, yes. So in this case, we would have a hash for P, right? It's our, I guess, the thing that we're gonna keep comparing to, right? So P hash
Mm.
equals whatever hashifying way. So just hashify, right? P, and then we loop through S. But since we're not looping technically through the whole of S, right? We're only looping until, oh God, stay here. Yes. So we're only looping until here, right? The index is going to be at A. This is the last index that we're going to visit. We do not need to go through C or D because the window is going to go beyond the string. And we know that like CD or like a 2-word letter is not going to be an anagram for a 3-word like string, not letter, right?
Yes.
So we stop at this. So it's going to be in a range, for example. Let's actually write some code. So loop through S, for example, range. We will start from 0. We will end in the length of S minus the length of P, because this window is the length of P, right?
We can
So
save one loop by making the conditions that we keep
not
looping
only
until.
one loop, not only one loop, you're gonna save a lot of loops. For example,
No, I
say
mean
that, yes,
I mean,
go on.
instead of checking the length, we can keep moving until the last element in our hash node is the last element. Like, oh, this is not a linked list. Excuse me, because there is no
No,
null element at the end.
no, but you can check with length. You can check
Oh yeah,
if something is bigger than the length, or you can just add it in range. We can both have like
yeah,
an if statement here, a condition,
yes.
like if blah 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 length is bigger than, or we can just not even like include it. It's gonna be in the range, right?
Yeah, also
And
considering, I think also considering that I'm wrong, considering the fact that the length is like when you get the length of an array, especially if we're talking about Python, it's not looping through the array and counting. No, it's the length is like an attribute in the object itself. Am I correct?
it's no,
Okay.
you no, the length of an array is the number of elements in the array. It's gonna give you an integer.
Yeah. I mean, when my idea was that instead of I wanted to like imagine that I would save when I want to get the length of s, I would loop through it and count. But I
No,
recall that when you get the length, you don't really loop anything. It's like an object. I'm sorry, an attribute
no, it
connected to
is
the.
not. It is not an attribute, I believe. It is I believe a built-in function that does that.
Yeah. I mean, this built-in function does not loop through the array, but rather, as
It
far as I know
does.
from C Python, no, if you run these advanced tasks of CPython, you see that whenever you have an array object, the length is an attribute in the structure of the array in the object itself.
Don't
If you remember these
I
tasks,
understand you. I understand you. I don't think it's the case here. It is not the same as JavaScript using, for example, like array dot length. It is not the same as this. It is like an independent function like array, right? And
yeah,
it does loop through it. It does. I believe the time complexity is O(n), so it
this
does loop through
particular
it.
one, I was like, we had the mentor who was talking about this one. They were looking at an algorithm and saying, if this is the case, if len does
Oh,
loop,
listen to me.
then why the what do we call it? The O? It's the O of one, or O of like n over two, not O over n if we're looping already.
I
Probably
guess
I'm
it
wrong.
is O(1), not O(n), as I thought.
Yeah, O of one,
Okay,
yes,
you're right.
not O of
Yeah,
n.
okay.
Yeah, yeah.
I still don't think it is an attribute of the actual array. That part I
Well,
don't
it's
think
actually
it
it's
is.
contained in the C Python code for the implementation of a hash map in Python. It actually
Exactly.
has len as an attribute, so you can just get it as part of the object.
All
Yeah,
right,
that's what I
okay,
meant.
okay.
I'm
All
sorry, I
right,
said an attribute. Excuse me.
I think it's called an attribute, right?
Okay, possibly.
Maybe correct. Yeah.
okay.
Thank you.
What were we doing? Um, I guess we were
We were
saying that we
looping
I
will.
think we now understand. I think it's time to jump to code. I think we understand the pro.
Uh, don't burn through the steps. Let me enjoy this. Okay.
Okay.
So
You like
so
write some pseudocode.
yes, we were right. We'll write the sort of code. So we said that we will not go beyond the string, right? So the range is gonna be the length of s, right, minus the length of p, because our window is the length of p, right? It's gonna be like this, and if our window is the length of p, then it's not gonna go beyond length of S minus length of P. For example, I have, believe, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 3, right? So 10 minus 3 is 7. 0, 1, 2, 3, 4, 5, 6, 7. And this index, this 1A, is going to be the last index that's going to get visited. Anything beyond that is not going to get included. All right? Okay. So we find a way to check for anagrams. So we said we're going to make a hash table, right? A hash table for our window. Now, the only time we actually make the hash table is in the first iteration. You either make it outside and use it inside of the function, or you just check if this is the first iteration, then you make the hash table, and then afterwards you keep just updating it. You add, remove, add, remove, right? So I believe if first iteration, then we make the hash table for our window. If not, if this is like in the middle of the array, so if it's else, then you just update the previous window hash, right? So what do we do in this update? We add the next element. So in this iteration, right, I am, for example, index is supposed to be 2. So I believe we will need maybe this, right? So this is our index. So at first it was at C. We made the hash table for this. We compared it. It is the same. It got stored. And then the index moved on to B. Now the window itself, the hash itself, is still in the previous window, right? So what do? We add this letter. This letter is 0 or 1, 2, 3. It is the length of the window. So I am at this index. So I will add the length of P to this index. So for example, I am at index 1. I'm going to add length of 3. So 1, 2, 3. But since the length has the x, or it doesn't start from the index 0, so we're going to add a -1, right? So in this case, we're adding 1 and 2, as if like going from 0, 1, 2, because this is the index that we want, or this is the element that we want to add to our window. So it is index plus the length of P -1. So let's do that. Add index plus length of P -1. That will give us this element to add to the hash table, right? So that is added. Now what do we want to do? We want to remove the element before the index. We want to remove the last element. So what do? Index -1, because it is before. We don't have to guard against like being at the end, because the first iteration, we make the hash table instead of actually updating it, right? So in this case, we remove index -1. Does this make sense?
It does. It does.
All right, good.
I'm gonna leave you
Then,
and get back quickly. It's for Esha prayer, okay?
so now we just compare the two hash maps or hash tables, right? And if they're identical, right? If they are the same, then you save the index that we're currently at, right? So in this case, this is the index that we're at. You save it to the results. And yeah, you just keep going and looping, and then you return your result. Does it make sense? Does anybody have any questions?
And so I think you can move on to the code. I think it's clear enough, right?
Yeah, we can.
Okay.
We sure can. Okay. I believe we will not be making many codes as I thought. So, okay. There are a few ways to actually make this hash table, right? There is Nyangasi's favorite ways is using counter from collections, right? This is an easy way to just you just give it your iterable, being like a string or a dictionary or just like an array or anything, and it will make a hash table for you, right? With like counter, an object, counter object, right? And you can
Yeah.
update it by using subtract, and where's the other one? Update, right? So you just give it whatever new letter or element you want, and it would add it to the already existing hash map, right? Or the counter object. We can use that, right? But it is not very fast. It is quite slow, and this update and subtract methods that they had are very expensive and they take a lot of time. Most of the like the fastness, I guess, was like 15-18%. So it is not worth exploring that. The second way is using this dictionary, right? Having like looping through P and then or S and then like manually, I guess, make the hash map, right? You just keep adding to it. The third way is actually an array. You can hold, technically, you can make the hash map since I guess the order of the letters of the alphabet is pretty known, right? And we have this constraint that all the elements of S and P are going to be lowercase English letters. So technically, we only have 26 letters or 26 characters that are going to appear in our S and P, right? So you can make a like an array, right? The first element of the array is always going to be A. The second is always going to be B, right? And we don't skip the negatives. The negatives, not the negatives, like the null characters, for example. In this case, we will have an array of length 28, right? With 3, 3, 2, 1, 1, and the rest are going to be all zeros. So like a way to know, for example, where to find B. B is always going to be index 1, right? You can have like a way to extract the index from the character itself using OR, like the Unicode, I guess, number for it, right? For example, let's do this. For example, or for example, A is gonna be come on 90, 97, right? B is gonna be 98, C is gonna be 99, D is gonna be 100, right? And you can get the indexes by just subtracting from this. So A is gonna be this 97 minus 97, which gives you the index of 0, right? And you keep going. So ord A or ord character minus ord A will keep giving you like 0, 1, 2, 3, 4 of any character that you want. So for example, ord, so this I guess is the formula. This should give us 0 because A is the first index of our array. For example, I want to put like G. G is giving us the index of 6, right? It's in our array, they're already positioned, right? So we just use an array instead of a dictionary, and I found it is faster that way to use that, but I guess we won't be exploring that, so I will just I just wanted to like give a different way to make the hash table, since the actual like logic of the code is pretty simple. The only I guess medium the reason they put medium is to make it fast, and I think this task or this problem requires like a fast solution. All right, so let's put this here, right? We have a result. We have this. So we can make like a pretty simple function, right? To, let's call it hashify. Let's give it like a string s, and you just loop through each character of this string and then record the occurrences of that letter. So we have like the is a dictionary, and then for car and s, you add that letter. So it's gonna be car plus equal, I believe. Yeah, it's gonna be equal d dot get, because we cannot guarantee the presence of this character in the dictionary, right? So for example, in the first iteration, the dictionary is going to be empty. You cannot just do this, right? For example, a is going to give you an error. So what you do is you use dot get, so you can give it a default. So that get character, and our default is going to be 0 if it is a new like a new character that we're adding to the dictionary. And then you just, what did I do? All right, plus 1, right? And then you just return. All right, so this is pretty fast. I guess we can add self here since it is a class method. And then now we can use it to hashify p, right? It's gonna be self dot hashify p, and then we loop through s, right? So for index in, and this is our range, right? We can just remove 0, don't need it. So the range from 0 to length s minus length p, right? And I might need a plus 1, but I'm not sure. All right. Let's do this. Yeah. All right. So if it is the first iteration, because for now we don't have a hash for our window, right? So in the first iteration, aka index is going to be 0. So if not index, we are going to have to make the hash table. So we can do that, right? So our window, let's go back to our window. Our window is the length of p, right? And it's going to go from the very first index, which is 0, to the length of p minus 1, right? So it's going to be from 0 to 3 minus 1, which is 2. So 0, 1, 2. This is the length of our window, starting from 0, length p minus 2, minus 1. So we will make like a window hash equal, and we can use the same function that we used. In this case, we're not gonna add like p, we're gonna add the substring or the window that we're gonna work with. Again, starting from 0 and ending at length p minus 1. But since this little operation excludes the last character, right? It's, you give it the first index and you give it the last index, but the last index is going to be excluded. So we just have to remove this minus 1. So it is S0 until the length of p. Now we have made our window hash, right? So if it is not the first element, right? If it is not the first iteration, we are in the middle of the array. For example, this is the second iteration. We will have to update it, right? Index is at 1. The array is still back at index 0, so we add, right? We add. We add as in we, I guess, increment the count of that element inside our hash, right? But we still have to make sure that, like this, we make sure that it actually exists before adding it. If it doesn't, it creates a new one. So it is technically the same as this. Instead of that, it's going to be our window hash, and the character is going to be s, the character is going to be this, S of this, right? So S. So this is the element that is this, right? This E that we want to add, which, as we said, is the index plus the length of P minus 1. And we can use that anywhere, right? For example, if this is our index, for example, then it's going to be index plus length of 3 minus 1. And it's going to give us the element that we want to add to our hash, right? So it is, where is it? So it is this, index plus length of P minus 1, right? And we get, again, the same element, right, with a default of 0, and we add 1. We're going to do the same thing for removing, right? So let's have this here, and here is going to be, here we have to make sure that the element actually exists, right? Here is going to be index minus 1, right? Index minus 1. Now, if this element doesn't exist, right, it's going to give us a negative. If we get this doesn't exist, it's going to default to 0. 0 minus 1 is going to give us a 0 in our hash table. We can, I guess, replace this with 1, so it becomes 0. It doesn't really matter because we're going to have a guard here, and we're going to check, because a funny little thing about Python is that it doesn't really recognize empty, I guess, keys as non-existent, right? So Python, if I have like C equals A1 and B0, and I have a D equals the same thing, but only has A, the actual non-null keys, right? If I do C equals D, it's going to become false, right? Because it still compares the fact that it already has a key or not. So to do this, we need to remove any null keys in our dictionary. So we check if this is like negative or 0. So if it is negative or 0, so if, I guess this, or we can just do this since we already know it exists in some sort, right? Whether it is negative or 0, if it is smaller or equal, or I guess just smaller than 1, we delete the key. We don't need it because it's gonna mess up our comparison, all right? Good. Now we compare the two hash tables. It's very easy. If p hash equals window hash, it is very simple. Now, if they are equal, then we save index to rest, our result array. The result dot append index, and then we return a result. Does this make sense? Yes? No?
Yes, it does. Yes, it does.
Are
Okay.
we calling index IND or IDX? Is
Yes.
it?
You're right. Yeah. All
Yeah.
right. Any other typos? I don't think so. So let's try.
The D.
Okay. So D is not defined because it is window hash. It's the same here. That's it. Okay. So the first case passes, right? It gives us 0 and 6. The second case is missing the last one, so I did need the +1. Since I said that this range and this thingy, they exclude the last element or the last, I guess, thing that you give them. So you have to add a +1 to include it or to remove it. So I believe this should pass if we submit it. And it passes 57. If we use the, as I said, if we use the counter, it would have given us around 15, would have been pretty slow. If we use this OR, it would have been really fast, around 90 even. So yeah, I guess that is it for this one. I hope everybody understands it.
Yes.
Okay. PacMan,
Would we take some time to try to solve it by ourselves, or you move on to the next one?
I mean, we just move on usually.
Yeah.
Maybe
Okay.
next time you would have gotten the leech codes ahead of time and attempted them to solve them like yourselves.
Oh. Okay.
PacMan, did you?
Let's see. Okay, so the first time I'm on the browser now.
Okay.
You'll have to excuse me. I'll try to make it as quick as possible. We're a bit behind on time, I guess. Um, okay, you can see my screen, I believe.
Yes. Finally, we do.
Yes.
Okay. Oh yeah. So I'll just begin with that small question that we had on how the Apache is implemented in C Python. So this is an ordered dict in Python. It's part of the collections module, and one of the things that it inherits is the dict that is default in Python. And one of the things that it gets from the dict, which is built in Python, is a get item. It gets a len attribute as well as a contain and a get. So I guess, can you see? You see what I'm saying? I need to zoom in.
Yes.
Yeah, okay. Right. So yeah, the next question you're going to be looking at, or is the next task, is going to be the LRU Cache LeetCode question. Let me just drop the link in case anyone was not seen it. Wrong app. Okay, so that's the task that we're going to be looking at. It's come on. Look at the so I don't know, is everyone familiar with what cache is? Anyone have a question on what caching is, what it does, why it matters? Still together, right? Hello?
Yeah, I have no problem with it.
We
I
could
No
understand
one
it.
has a problem with the cache.
It could help if you like made a quick summary of what it is, what it does.
Okay. So now, keep just let me know. I'm gonna be switching screens a lot, so let me know if you need anything. If just try to use your mic so that I can be able to keep up. So yeah, the question does require a bit of context. So we'll just open and we do get a link to Wikipedia. So caching, what is caching essentially? So what you're saying is, so there's this thing called latency, right? And latency is basically the fact that it's always going to take a certain amount of time to move information, or a packet of data from one point to another. It would be nice if you did have it, but it exists, and there's only so much that you can do to eliminate it. But every other thing that you do, or any other code, any other process, any other algorithm that you add on top of what you already have increases the latency or the amount of time it takes for that task to complete. And I'm not making a lot of sense. Let me try again. So let's say you're trying to make eggs for breakfast, right? If you want to make those eggs, you need to first acquire the eggs. So you go to the shop, you buy the eggs, you come back. So it takes you a certain amount of time to go from your place of residence to the shop and to get back. So that's what we're calling the latency in a sense, right? To complete that information change, okay? So one of the things that we can do to make it faster, or to be able to enable you to make your eggs faster, is instead of having to go to the shop every time you need to make eggs, you just keep them in your kitchen, right? You keep some eggs in your kitchen. So anytime you need to get an egg, you just retrieve it from there. So we have eliminated an extra process or an extra trip that we don't have to make anymore, because we have a local copy of the items that we need, right? Does that make any sense?
Yes.
Yes, it does.
Okay, so that's the same concept with caching. So caching essentially means that if there is a network request that has to be made, if there's a read process that has to be made to your disk or your storage, if there is an API call has to be made as part of your process, what you can do is, the first time, go out there, do your API call, make that network request to Google to get that information. But the next time, instead of just running to go and make another API call or to go to Google again, first check if you already have that item. And how do you know you already have that item? If you've already kept a copy of it. So first check if in your local copy, in your local space, you already have that item. If you do, then you just retrieve it from there. If you don't, you go get it from the original source, keep a copy, and then do what you need to do with it, okay? So now that brings us to the next part. Actually, we can look at it here. The next part is, what do we do when we run out of space in our local cache or our local store, right? There's only so many eggs you can keep in your house, right? So what do you do? Like, how do you decide which ones to throw away and which ones to keep? So that sort of determines your cache replacement policy, or how you're going to replenish your supply when you run out of, when you fill up your capacity, or you fill up your local store. Like, how do you respond to that? How are you going to determine which items are going to get removed so that you can add a new item, okay? This is where we get the LRU cache, right? So the LRU cache simply discards the least recently used item first, okay? So there's three things. Did I drop out? Wow, sorry about you.
Can you quickly hit Alt Shift D to just open dark mode, because our eyes are like dying.
I did not do that.
No, I mean, and for the browser, it does it automatically. Nothing you to have a
So that's okay. Let's do this. Let's inspect. So
okay.
this is so yeah, let's say, for example, so every time I try to access this Wikipedia page, which is a static website, it has the same information every time. So if I refresh this page, and the browser is that we can disable the default cache that the browser will always do, right? So the browser will always try as much as possible to speed up what it's doing, which is web browsing, by saving a local copy of your pages as you surf through the internet, okay? And so let's see what happens when you guys see what's happening here. You see all these network requests and all this information is being fetched, right? These are all GET requests going every time. If I was to enable the cache, you'll see that I just click something there and I try again. Okay, so we have the first request. And now that's the only thing happening. Despite how many times I refresh, it's only getting so much information, right? And we can see that now we are getting 3 or 4 requests with 3 or 4 response. I don't know if I'm doing too much, but you can see the browser has been able to save some information, and we are getting a 3 or 4. 3 or 4 is HTTP status code to say sorry, not modified, right? What does that mean? It means that the requested source has already been retrieved. No need to do it again. It's already saved in the browser, in the cache, okay? I don't know if this is just too confusing. I should stop. Just like, it doesn't make any sense.
Yes, actually.
Yeah, so the more you go through the internet, the more your browser is saving your pages as you go through. And you're trying to save the last page you were at. So if I was just at this page, then you'll keep a copy of this page. And go to another page, see you save another copy. At some point, we're going to run out of storage. So we need to determine how to replace and how to remove which items so that we can keep adding the web pages. So in the LRU method, we just keep the least recently item is being discarded. The most recent is kept. Okay, so I guess that's caching explained in a sense, right? So we're good, right? Now we can look at what the problem is. The problem is we are required to design a data structure that follows the constraints of a least recently used. Least recently, we have seen, simply means, it's Wikipedia's fault. It's Wikipedia. Sorry. I'm doing too much again.
Now you can hit Alt-Shift-D.
Okay, you're happy?
Yes. Yeah, I'm happy now. Thank you.
So where's the LRU? Yeah, so all of this is, so there's different ways that you can decide how to retrieve and which ones to delete. And LRU, this is cache replacement policies. Why am I here? I'm supposed to be seeing LRU. Is it here? Oh yeah, so least recently used, this is the one. So it discusses the least recently used items first and keeps track of what was used and when, right? Which is cumbersome, as they tell us. So we need to be able to keep some sort of who was here first and who has been most recently accessed, okay? I'm going to try to move faster. So I have to implement, so we don't need this anymore. So the LRU cache is going to initialize. So the first thing that we have to do is implement this cache, this class. And what it's going to do is, number one, create a class, which is going to be our class cache, which is going to be given a certain amount of space. So we said that there's only so much space that we can have. So we're going to be told what is the size of the cache, right? How much information do you want to save? Ideally, you want to have like not so big that it's going to be a problem to maintain, and not so small that you can't even do anything useful with it, okay? And it's only going to be positive, so that's the capacity. And then we're going to be doing two operations. We're going to have to get from the cache, and we're going to have to put. So get is simply return the value of a key from the cache if it exists. Otherwise, it's not there, so return -1. So we're going to see how we are going to go about implementing this. And the second part is we have to put. So put is simply insertion, right? We insert a key value into our cache, this LRU cache. And we're going to have to do two things, right? So if the key already exists, you have to update its value. Right? So let's say you have saved 1 and you have mapped it to letter A, and then someone comes and gives you 1 again and it's mapped to letter B. You have to update that value from A to B, right? So if the key already exists, you need to update. Otherwise, add the key value pair to the cache, okay? If it exceeds the capacity, this is the final part, evict the least recently used key. Okay, so this is where the LRU comes in. the replacement policy is the least recently I used item is the one you're going to be replacing. Functions get, and then this is the final part, which is crucial. The functions must each run in O of 1 average time complexity. So already spoken about latency. So now what we are saying is this is a caching mechanism. It's supposed to improve the performance of the overall performance of our system. So when we're doing this process, we want to make sure as much as possible that this caching algo that we are going to introduce into our already existing program does not add even more complexity or make our application or process or our program even slower by introducing its own latency or taking its own time to do its thing when it's supposed to improve our performance. So we want constant time or O1, so instant access, instant deletion, and instant search. Okay. Now the way we're gonna implement this is by using. Hold on a second. Just a moment. Okay, sorry about that. Yeah. So the way we're gonna implement this is, so now we have to go to the Excalibur and look at why. So anyone have any ideas so far? Anyone have any thoughts? Anyone have anything they're thinking?
Well, I have a question first. Is it
Okay.
normal that it's all the time asks for O of 1 in average case, not worst case?
It depends on the question. So in this particular one, they want O of 1. Sometimes you may not need it, sometimes you need it, but for this particular case, they want it, and it kind of makes sense about it. We are trying to optimize a system. This is not an algorithm that does something or solves a solution. It simply optimizes part of a process or part of an algorithm or part of, you get. We're just trying to optimize a system. So if you're going to optimize, don't introduce your own latency. Don't introduce your own. Actually, I have a visual. Yeah, you get what I'm saying. Like we need to. Sorry, light mode again. Oh my god. Just bear with me for this one. So this is just like latency numbers every programmer should know. And it's a bunch of numbers over the years as they have changed. And what you have is you have a cache on your CPU, right? Right on top of the CPUs is the L1 cache.
Yeah.
Right? You have another, and then you have the L2 cache, which is slightly bigger and slightly slower than it, but these are still extremely fast. This is nanoseconds for L1 cache. Okay.
Yeah.
So you need to make sure your cache is extremely fast at every level. But as we go further into the system, it gets slower and slower because now you're doing main memory references. In this case, you can see it's faster for the CPU to get something that it needs from the L1 cache than to go to the main memory, which is the RAM, which takes 100 times slower. Right? You can see this is 100 nanoseconds. This is 1 nanosecond. You see, that's tremendously faster. And then you go to the next step, which is reading and retrieving from the SSD, and even the slowest part, which is sending information over the internet. So you have to wait for the packet to go to where it's going, for example, to wikipedia.com, and you have to wait for it to come back. And this is the slowest part of anything. So making network requests is the most expensive call that you usually make. So this is what we want to cache as aggressively as possible without introducing our own latency, right? So that makes sense, right?
Yes.
Yeah. So
I suggest we take just only 5 minutes. By the way, before I suggest this, do you normally like post the problem before we start?
Oh, yeah, absolutely. We usually have the problems posted on the channel, on the general channel. About, was it 3
But
hours, 4
since
hours
Moses
ago?
abandoned his post, we have not been keeping up with what we should be doing.
Yeah, the posts that I've made did not include them, but I will make sure to include them in future posts.
Okay, so if this is the case for this one, I suggest we take like 5 minutes holding our thoughts. That would even like make better ideas, and also interference will be like kind of less or something. But let me ask you first. I see like initial thoughts could be like stacks and queues probably, but let me ask you: is
Oh, yeah,
there's a data
absolutely.
structure in Python that have this push and just like JavaScript, you can push from both sides? That would
Yeah, absolutely. You have an ordered deck, you have a deck, you have which one else? Sabah, mention more.
I mean, you can access it from both ends. That's what I mean.
Yeah, essentially they are implementations of doubly linked lists. So you can get it from
Yes.
the back or get it from the front. It's
Yeah,
implementation of a
that's what I
linked
was
list.
thinking actually too. Linked
But
Yeah.
list.
we're thinking of
I believe a queue
leveraging this, not making.
also has an easy front and back, like left and right.
Yeah,
Yeah.
Yeah, it does.
queue, but
The Deneb and the
we
saddle.
have
Yeah,
to.
absolutely.
If it's directly, then you're dealing directly with the processes, not like new and old, like new coming processes, and you're pushing the others. But what if you're using some of the things in the data structure itself? That's why
I think
X
Q
and Qs
is
will not be the direct. It will be leveraged, but not the direct one. Okay, let
Yeah,
me close
absolutely.
my mic.
You're on the right track.
Yeah, let me close
You're
my
on the
mic.
right track. Just keep
Yeah.
going. You're getting it. You're getting there. So we are going to use W linked list, and that will enable us to access the item from both ends, right? So we're getting an item from the top of a linked list or getting it from the tail. So let's say the head and the tail. Its goal is going to be all of one, right? So the issue with the
So
linked
we have
list
to.
comes in when you try to get an item, let's say in the middle of the linked list, right? That's when you have to go through each and every item, right?
I mean, if well, it's about insertion. If it's about
Yeah, exactly.
insertion of data, we could have this messed up data structure that it's like it's implementing W linked list, but at the same time there's an array. Like it's kind of the hash, this hash map, but it's not really a hash map. So you can access
Yeah,
both
that's
ends, but at
the
the same time, when you insert something, you can insert it at the right index, but you have to leverage directly to be a problem because you need to search for the things
no. So we
that are
won't need to
already
search because
in the
we
cache.
already have the hash map. To search for it, we just get it from the hash map,
Yeah.
and then to insert, we just insert into the linked list by just switching the pointers. So let's look at it. Let's look at the solution or a visualization of the problem. So yeah, it's so we have to get some way of getting items basically organized so that they're become one after the other, right? So that if I have an item, what's happening? Yeah, so if I have an item, let's say this is the first item. If I add another one, I want to be able to add it to the next part of the linked list. If I have another, I want to be able to add it as well and continue that way. We'll add the arrows later. But we also need to find a way to be able to access, let's say, the third element of this linked list without going through 1, 2, 3, so that I can be at this point, right?
I think yeah, we need this,
So
and we need another functionality to keep track of like we have a set of elements. We have four of them, so we need to keep track another structure to keep track of the number or the index of the elements that have been used, not the elements itself. So we don't keep
yeah, exactly. So
switching them, but we switch the numbers of them. Like we separate the data itself from the indexes, something like that. I'm keeping my head around this.
okay, you're on the right track. That's a great idea. Let's move this
Okay,
one.
okay.
This one decides to move.
Relax. Oh, thank
Okay,
you.
so now let's get that. Say like key. Say we have a hash map, right? We have a hash map up here. And what it's going to do is going to have a key value pair, obviously. So we want to be a value. And what we're going to store is essentially the same items that are on the linked list as keys. Let's just not draw the arrows right now. Let's just keep in mind that this is a linked list. So if this linked list contains the key value pair as information, let's see, as one, and one. This one has 2. This one has 3. The key 3 contains the value 4, and this one just so that we are sure that we're not doing something. The key contains the value 123 or something, right? So what we're gonna store on the hash map, which corresponds to this linked list, is going to be the address, right? The address of this node. And we're gonna say that one is 1. So the key 1. Okay, I'm misbehaving. Say 1. Yeah. 1 will contain the key on the hash map. So this is going to be like an implementation of the hash table, the classical one. The one, this one we're going to say 2. And this one we're going to say 3. Are we still there?
Good.
Okay. And this one is going to be 4. And for this key, the value that we will store is a pointer to this node on the linked list. Okay. For the value for the key item 2, its value is going to be the pointer to this node. Same thing for 3, the pointer is going to be the value to this node. And for 4, it's the pointer value to this node. Okay. Are we seeing what's happening? Then this one, the arrows will come in.
Yeah, it does make
As
sense.
a W.
Yeah.
Yeah, so we're seeing what's happening here. So now let's see how it helps us, or if it helps us in any which way. Right, so it's a doubly linked list. It starts somewhere and it ends somewhere here. So in order, so this is, let's say this is okay, so we just need another node at the end too.
Sorry, are we solving it now?
Oh yeah, we're gonna go through it.
Wouldn't it be better if we just get like an overview of the solution first? Like, not really a pseudocode, but because I feel like I'm kind of lost. That I didn't really make my head around it. Like, I'm thinking.
Okay, so let's just look at what this does, and then we can see if we make any progress.
Okay.
Ideally, we would want to be able to finish the session with all the problems solved, so that someone can just, and then the recordings will be uploaded also to YouTube, so you can just go and look at them at your own pace. If you matter of switching the pointers and creating a new point. So it's going to give us the preservation. It's going to preserve the order in which items were created, right? So that was we get from a linked list, right? And additionally, accessing the items or inserting and deleting from a linked list is same thing. It's just going to be switching the pointers to insert or remove an element. So the linked list preserves. So when we want the least recently used item, we don't need to think. We just know it's this item, the latest one to be added, right? And if we want the most recently, we know it's the least recently used. It's gonna be this one that we just added. It makes sense. So we're going in this direction. So if I add an element, it comes here, comes here, comes here, comes here. Any more additions simply keep piling up at this direction. So that gives us the order preserved. So we will always know which is the least recently used, but which is the most recently. When it comes to retrieving, we're told we need to if the number of keys exceeds the capacity, evict the least recently used key. So if we need to evict the least recently used key,
We will go this
just
ahead.
come here. I will just come here, delete this one, remove its register from the hash map, and all is well. And we can add a new item, right?
One question,
We
So
if we were to add update a key from the middle of the list, how do we remove it from the middle and add it to the end?
I think we don't remove it. I think we just switch it with head. If we need to if it's used mostly somewhere,
yeah,
I think we just switch with the least
yeah,
with the most used. So switch places.
yeah, exactly right, man. Thank you very much. So
You're
we can see that this key points to this node. So if I need to say that someone has tried to get the value 3, so that means you have accessed the element, so you have used it. So in that sense, this is now the most recently used node. So we need to be able to take this one and move it to the end of our linked list, right? So all we have to do is update the tail pointer. The pointers are embarrassing. We move this one to this position. We don't need to update its value in the hash. We just need to switch its pointers to have it now point to the tail and these two to point to each other. And it's a node. Should have used this one. So this is a doubly linked node. So yeah, so we'll update the pointers to have. Okay, this is becoming a bit of a mess. So let's actually just do it in sequence so that we see what's happening. I think that will be better, right? Are we still together? Or is everyone completely lost?
No. I think I totally get it now.
I think it
Yeah,
will be
yeah,
much better if we just start writing the function.
yeah.
Okay.
But it's starting to make sense.
Okay, so let me just clean this up a little bit. And
So
then,
essentially, we keep a hash of the input that we receive, and then the sequences we rely on a link to keep the sequence of who of the sequence of recently used and mostly used and
yeah,
yes.
you're absolutely right.
Oh, right.
Okay. So that's what we're supposed to be doing. Okay. Okay, so we need, what do we need? First thing first is we need to create cache of size 2. Cache of size 2 for us is going to be this hash table. And let's put, where's our node? And add a node. Let's make a node for our linked list, right? So our linked list is going to have a W linked list with a forward pointing and backward. So node.previous and node next. Okay, that's just a node, and this node is obviously going to have a memory address. So let's call it something like OX1. Okay, this is OX10. Makes more sense. Good. Yeah, so that's the node in memory just relaxing. Okay, so now let's begin the process. I need to move this thing. Okay, so it's just there. We've created a node and we've created a hash map. So now we need to start the process. So the first thing we're going to do is we're going to create a new cache of size 2. So ours is just going to be a hash map. It can be empty, doesn't need to be of size 2 or anything. The first thing we do is we put 1 into the cache. So save 1. That's all it all. Save 1 into the cache. So to create this cache, we have our map, and we have 2 nodes. Just by default, we're going to create 2 nodes to begin with, and these nodes are going to be, to measure that, the head text. Head node and tail. Okay, so this is just housekeeping duties. We just want to keep track of where we begin and where we end. So first thing, put 1. So we are currently, we're trying to put 1 into the cache. Okay, so in order to put 1 into the cache, we just need to insert a node, and it's going to keep the value 1 1. Okay, so it's key value pair 1 1 in the node. So we get a node. We have a nice node that we have created here, and we insert it. We make a, should I move it or make a copy of these? So this is the first step. We want to insert 1. So we take this one and we update its pointers so that we insert a node here. Just a bit more space. Okay, so now we have inserted a new pointer, a new node, and the only thing we need to say is that the value 1 now contains the memory address of this inserted node. Okay, so up to there, we have now inserted, this should be a different memory. So OX should be 12 now, since this one is OX11. Let's see. Okay, so we have inserted a new node, and it's going to have the value 1 1. Okay, so that's the first part. We have just inserted a node. Okay, the next part is insert another node, and its value is going to be 2. So cache is now supposed to have 2 2. Sorry, this one should have been empty to begin with, and then we insert as we move, but let's see what happens. So same thing, take this and we We insert another node at the end. I haven't to my template. So we move this one. We put the new one here, which is going to have the value 2, 2. This is node number 13. It's on 3. Okay. Now we move to the next step. So up to, and then this pointer, obviously, this hash is going to point to this node. Just going to be a pointer to that. Okay. And then we do the next step. So we've completed 2 steps. And our cache does contain 1, 1. The next step is to get 1. Okay. So how do we access an item from a hash map? All we have to do is hash and hash map get value. So if I have to get 1, I'm just going to come here and say get this thing and get the corresponding value from the linked list, direct memory access using the pointer, right? I'll just come here and get the value from straight from here into the node. But additionally, now that this node has been accessed, I need to update the fact that we have used this node. So it needs to be now the latest node. So we need to take the whole thing again, make a change to have things going on. Okay, so the same thing, the only thing we're going to do is update this node to come to the end. And in this case, it's simply change this pointer to now point to this memory location. Change this one and now point to this memory location. Okay, so far so good.
Yes.
Remove this and bring it here. Okay, so now the tail, instead of pointing to this node, the tail will this one. But I don't want to do it here because it's going to be messy. So let's just say we have removed it and we brought it here. So we're just going to update it by moving in here. Okay. And so we're just going to update the pointers. So instead of this one pointing to this node, now it points to this one. This pointer now moves to this point. Okay. Thank you for the friend request. We're booming. It means we're doing well. Okay. So now the only thing we have done is update the pointers, and this one will still be pointing to this node. Okay. And so now, when this whole operation does not take any extra time, it's just switching pointers around. So the fact that we've been able to update the records to now reflect the most recently used item has been done. And we can return the one from here. We can now return the value, which is 1. Okay. So should we continue? I'll just use this to show.
One interruption, please. Wouldn't you need to
It-
traverse the linked list to actually find your node? Wouldn't that not be
That's where the hash. That's where the hash map is coming in. We're just gonna get whether or not this key. We're just gonna get whether or not this key exists in the hash map. Okay. I'm going to try to get this key from the hash map. I'm not going to try to get it from the node. It's on the doubly linked list. I'm going to try to get it from the hash map. So I'm just going to say get from the hash map. Is 1 in the hash map? 1 is in the hash map. What is the value of 1 in the hash map? The value of 1 in the hash map is this node, which contains our information. Okay, so I can say key value key dot key. So I can say this node dot value is gonna be 1. Node dot key is gonna be 1. Okay.
All right, that makes sense.
Straight from straight from the hash map without having to traverse the node. So now that's what the hash map is giving us. It's giving us direct access. So searching becomes O of 1 because searching in a hash map in Python is O of 1, right? Or retrieving a key or accessing a key from a hash map is O of 1. Okay. Wow, that is the time. Okay, let's continue with our small process. Where were we? Okay, so now we have completed the get. Now we can return 1. The next part is put 3 with the key 3 with the value 3 into. So we're supposed to evict 2 and add 3. So I'm just gonna copy and yeah, so let's just use, let's just say that this one is 2. This one is, no, it's just too messy. Let's use this one. Just use this one. Try to clean it up. Yeah, so this is how our hash map looks like now. Or our hash table actually looks like. And what we have to do now, okay, let me just not even do that, is add a new item, okay? But what have we been told? We've already been told that the capacity or the maximum size of the cache is 2. And what do we have? We already have 2 items in our cache. So we need to remove an item. This is where the replacement policy or the eviction policy comes in. Okay, so we need to remove the least recently used. And the least recently used item is always the one at the leftmost, in this case, the left side, or this one, which is next to the head, is this node. Okay, so this node has to be sacrificed so that someone else can come in. So what do? We, okay, this is messy. So what we do is we simply eliminate this in the way you would do for pointers in a linked list, which is away. Oh, sorry, that's the wrong one. So let's put 2 here. This is how our hash map looks like now. So 1 is here. This arrows just, you know what? Because now this one is here. This one is here. Double crossing, but let's just make it work. So now we need to remove this element from the linked list, right? So all we have to do is switch the pointers around again. Same way we were inserting, the same way we're going to delete. Just switch the pointers around. We just take this node, remove it, and join the head to this one, and do the work also some housekeeping in the hash map as well to remove this. Okay. So now our list only has 1 item. So now we are free to add another element to our beautiful hash table. So we're going to add 3, which is just another and 3 is now the most recently accessed. Text 3 in 1. So now 3 is in the hash table, so and 3 is going to do, yeah. So I guess at that point we get the idea. So we're going to do this constantly. I don't know, is anyone ever any questions? So you see how it's going to be going. So we're going to be doing this constantly. And when we do the next process where we have completed adding when we have exceeded the capacity. So we simply evict 2 and insert 3. So that one was clear, right?
Yeah, this one is gonna be easy.
Okay. And the same thing is, and when you try to get 2, obviously it's not there, so move on. Return -1, put 4. Put 4 is just going to eliminate this one and insert 4 here. Same for 3. Okay. We're good. So we can move to Z code. It's a bit late.
We can.
Okay, absolutely. Thank you very much. Are we still here? Okay. No one has any questions. Okay. Oh, wow. So now we have to do the code. Where's the problem? Okay, so the first thing we have to do, obviously, is create our node. Do we need visuals, or we can still remember how it looked like? So, our node. So our node, we said our node. Let me try to keep these two side by side so that we have an idea of what we're doing. This one is going to be so okay. Yeah, so our node basically contains the key value pairs and the back pointing pointer and the next pointer, the previous and the next pointer, right? So that's fine, right?
Yes.
So we can go about definite results. We're gonna have what? We're gonna have
It should hold a value, right?
oh, yeah, absolutely. Key value pair. Yeah, so we're gonna create as a key value pair, and inside the key value pair, gonna have yeah. So we'll save that in cell the key so dot value. Okay, wonderful. What else? We need the back and the forward pointing cells dot previous is equals to for now none since nothing cells dot next. Equals to I think that's it. That's fine, right? So that's our node. It's a valid node. Previous, next, the key value pairs, right? Memory address will be maintained by the CPU for the program itself. Okay, so now this is where we implement. Yeah, so we need to now create this hash structure, this data structure that we're going to be using. So it's going to have a node. The node will have a head. So it's going to have a head node, a tail node, And what else? I think that's it. Also, we need a capacity and a way to create the hash map. Hash map. Okay, that's clear. So let's do that in code. So self dot max size is going to be capacity and self on head. So we do that. No, so that is equals to a dict and that head. That should be a node, right? A node, and then you're creating a node. You have to send a value there. Let's just create head with 0, 0 and self dot tail equals to node with 0, 0 as well, and we link them. So self dot head dot next is equals to tail and tail.
مش دلوقتي خالص مش هعرف.
Sorry. The tail dot previous. I call it previous, right? The head. That's clear. We just created this part. So this part. So we created two nodes and we linked them so that we have like our starting structure. Okay.
Yes, PacMan.
Positive affirmations go a long way. keeps the thing going.
All clear, well, all understood. Go on.
I'm having
Now,
a query here. You can hear me, sorry,
okay.
right?
We
Yeah,
can
I'm
hear
wondering
you.
if there's a specific purpose why you didn't make it like what we do normally and see that we just don't have any tail or node. The node that like the first node has a back pointer of null or none, and the vice versa for the end. There's a specific purpose, or just like it goes like that with you?
Pardon? Let me just say that again.
Okay, I'm wondering why you did make a specific node called head and tail and gave it the value of 0 instead of like having a just making the first node. The linked list basically is empty, and once you enter something, you make it like you make some like you give it the back pointer of null, and if it's at the end, you give it next null pointer is null. Like we do normally with C. Is there a specific reason you did that here? Or you didn't do that here?
Okay, if I'm understanding, you're asking if I didn't just create like a head node and then start using the linked list, right?
Yeah, I see here you're making a variable called self.head and self.tail and making it point to a node, like an actual node in the memory, not just a pointer to the first or the last node. Do
In
you
this
have a
part, I'm just initializing the structure so that I'm just creating two nodes. I'm just creating two nodes. Here, this is just like the structure of the node. So any node is just going to have a structure similar to this. So all the nodes are going to look a lot like this one, right? They will have a key, a value, and I just put it, yeah, it's going to be messy.
I mean, why not having it being initialized to 0 or to none? And when you add a new node, you make this variable self.head point to that node. And if it's at the end, you make self.tail point to this last node without making an actual node. You get what I'm talking about?
So I do need the actual node because I need to be able to access the back and the front of the W linked list, right?
Okay, I think it's easier. Yeah, I think it's easier. Yeah, I think what you made
Right.
is easier. I'm sorry, I was just asking if there's a specific reason in the logic or just like to make it easy or something. Because I'm not used to
Well,
that.
okay, I'm not sure if I'm completely understanding your question, to be honest, but the whole idea of using the W linked list was to be able to access the tail or the beginning or the end of the linked list as efficiently as possible. So I don't need to iterate through the list to get to the end or to get to the
No,
beginning. So by giving myself,
he is asking
uh-huh.
why did you initialize them?
Then
Why
why
did
did
I
you
initialize them
for
with
the head and the tail? It could be a linked list without those two and just the middle content.
this part?
Yeah, he is asking
Or
why did you initialize them? Why didn't you leave them null?
I could have them null.
Yes, that's
I do need
exactly
the
what I'm
node.
asking. Is
Because
there
the
a specific
capacity might
reason
be
you did
like
that?
0 or 1. So
Okay, so which line are you referring to? Someone point me to a line.
13 and 14.
yeah,
Okay,
Is
so
the
there?
this is
highlighted one. Let's
Yes.
say the capacity is 1. So you have only the head is the tail, but you initialize 2. So
no. So we're not gonna look at these when we are trying to. These are simply housekeeping duties, so they're not gonna be counted as part of the capacity of the links of the cache, right?
But the linked
These are
list
just
yeah,
for
I
ease
mean
of
he's
access.
just
Have just
asking why
that
did you
one.
initialize them right now?
Yeah, it could be why you couldn't have like the linked list with that one node that you have in your capacity without having a head or a tail.
But
Okay, so
it
let's see
could
what
count.
happens.
No, let him continue like that. My question is already answered. There's no specific reason for it. You can keep continuing like that. No,
So
answer.
I'm just,
Keep with your logic.
I was referring to this when, like, what to try to recreate the exact steps that we carried out here to have
For
initialize so that when we're
demonstration
inserting,
purposes only.
we can just have it here where we don't need it actually. Right? We don't need it, but we're gonna have it so that we can make our lives easier. Okay.
Yeah. Instead of making like F statements, is this the last one? Is this the previous one?
Yeah, exactly.
Yeah. I think it's a good one.
Just for making your life easy, not
Yes.
nothing too.
It's nothing related to the logic of the algorithm itself.
Yeah.
Yeah.
Okay.
Thank you.
So next part is
Yes.
we need to. So the next thing we did is a put. Sorry. So let's look at put, since the next thing we did was to put. So in order to put an item into a linked list, we need to. Anyone have a problem if we create a new node here?
Oh, we're good.
Here, and we give it the key value pairs here with a key value, right? But additionally, we have a few things that we need to do. It's just for housekeeping. We need
We
to
need to
check.
check the capacity to make sure we
Yes,
still within.
capacity. Make sure we should have done this in the pseudocode first. Not exceeded. And if we have exceeded, if excess, use least recently used.
The hit.
Yeah, use the algo project policy or policy to remove the node, right? Or create space for the new node. Okay. Well, okay, this is gonna be interesting. Yeah, so first thing, put sorry, let me just check something. That's here. Okay, then should have put date the value of the key. Okay, I'll just take this. Okay. So update the value if it exists. Otherwise, if the number it is the source. Okay, so
عشان هو مش راضي يشتغل. I'm sorry guys, I'm sorry, excuse me.
pardon?
I was talking while the mic was on. I didn't notice that, so I said I'm sorry.
I'm sorry. So if is in key is yeah. What do we do? It is in the map. We update the value. So we're gonna need some update value in the linked list, which we said is just pointers, right? No. That would be that. Otherwise, so add the key value pair to the cache. So go to sorry, this is a hash.
You call it self to hash. Yes, I have been just checking this.
You need to add the key value pair. So hash key is this will require. I will need to create a new node. So create a new node, and the new node is gonna have the key value pair. So value. And otherwise, if the number of keys exceeds the capacity, so if shouldn't this be before? Should probably check first. If the number of keys exceeds the capacity from this, so plan that map. Do I keep calling a hash map? Should I call it a hash map? The length of hash map is greater than max size. Max size. Elect the least recently used key. So least the LRU. So the least recently used key, we're gonna have to get that from. We're gonna have to remove it from. So we're gonna have to remove it from the thing. Sorry, you'll have to watch me typing for a very long time. Hash remove. So that's gonna be right? That's fine. No, we're gonna get it first. Okay, so let's do this. Let's implement
I
this.
don't.
We have to implement
It's just
the
you're not the hash, not the key, but the one in the head, the least the head.
yeah, exactly. So we'll have to first get it from. Yeah, exactly. You're actually right. So node. So a node is going to be self dot head dot next, right? Yeah. So head dot next is the one that's gonna have our value. Then we delete this node dot e, and we need to remove it from the list. So we
I
need
think
to.
the removal will be just maybe a switch like brev next, and you know the switch in the Python.
Wait, you have a built-in switch for
Not
nodes in Python?
built-in
That didn't
switch
click.
like when you have A and B and you want to switch the value, you say A and B equal B and A. This is
No, but we need to just move the pointers though, not the values. I think that would switch
yeah.
the values.
It's not the value, but it's like you point it to.
You
Okay.
can do the same though.
You can do like brev.next and next.brev, and you switch it.
Oh, so why don't we just write that here? This move shells. What are we removing? We're removing node. We just need a node. Right? And when we get a node to remove, oh yeah, so now we can say node dot. You said node dot?
Yeah, not
So
brev.next, I believe will be.
yeah, node dot
Node.prev
becomes
dot
node.
next equals node.prev dot next. And oh, what happened to me?
Not
Equals node dot next.
.brev. Yeah.
Yeah.
It's always lovely.
Node dot prev. Right.
In C, we would have had to use a temp and just like do a lot of switch around.
Yeah.
That was a
Could
nightmare.
have done this in one line if we wanted.
Node.prev.next equals
Yeah, node dot prev dot next becomes
node.next.prev equals node.prev.
Yeah, exactly. Yeah.
There is an easier syntax here. Just node.brev.next, then you get a column, and then node.next.brev.
Minna, it's complicated
yeah.
as it is.
This okay. This is not complicated because you change it the next. Now you change the next. So when you do it again in the next line, it's complete. It's already changed. That's why you do it in the first in one line.
Yeah. See, this is why we have you.
Because other way you would have used a temp. It would have been easier. Yeah, I think that
Okay,
is.
that's fine now.
Sabah, you are the queen of complicated. Is this correct?
I think I think so. Yeah.
Okay.
Okay. But we could have done the previous one first and then done the next one. Anyway, so we also have to insert a node. Who wants to have the honors of inserting a node? By inserting a node, we only insert at the end. So who wants to have the honors of playing with the pointers?
Tail.prev equals node and no. tail.prev.next
Okay.
equals node, and tail.next equal. I'm sorry, tail.prev equals node.
Hold on, say that again.
Okay, tail dot tail.prev dot next equals node. We will edit this, but let me just do it now.
Yeah, we'll edit. Yeah.
Yeah, and I'm just imagining it. Equals
Let's
node.
not imagine. Let's look at it somewhere
Yeah,
here. So
equals
inside one
node.
is going to be. So let's say trying to insert here.
Sabah is saying
What we
something.
will do.
Yeah,
Sabah,
so
say
it
something.
is tail.prev equals node,
Yeah, tails dot
and
Yeah.
prev equals
No,
node.
and
but how you
tail.prev.next
will?
also equals node.
But you now you missed access. You don't have access to the actual last one. So how you will
Wait,
make the next
we
pointer
will
points
do
to
the
the node?
same thing we did before with the syntax.
Next,
Prev.
I mean,
That's gonna be node dot next. Which pointers do we need to preserve so that we are safe?
I mean,
So the
where's
prev.
the last element?
So I believe
Hang on, why we're not using
tail.prev.
self dot? We're using just node. Is there something I'm missing?
Pardon?
Yeah, you're saying no. Okay,
So
self
tail.prev.next equals node,
dot
and
tail.
also tail.prev equals node. And then the tail itself, or the node itself, would have the prev and next. So the
Okay, so I've just taken
tail.prev.next,
this pointer. This is the next and this is the previous
yeah.
pointer, right?
So
So now we can come here,
tail.prev.next
prev
is
dot
node,
next.
and
Yes.
then tail.prev equals node also. Right?
Pardon, say that again?
No, keep
Tail.
that. That's correct. So both of
But you
them.
have to
Okay.
put the previous of the node equals to the last one before you lose access to it.
Exactly. Yeah. Tail.prev.
Tail.
.prev.
Wait, let's
Just
look
that.
at this.
So it's the prev of tail that is gonna be linked to node. Yeah.
This is the same line.
No,
So
but
these are
without
two
the
the same
no,
lines.
without the next. It's just tail.prev. It's the tail itself that's gonna get attached to node. And both of those, I
So
guess, are in the same.
tail dot
Yeah.
prev, tail dot
Tail and
prev dot
prev.
next. So this pointer dot next is gonna be node, absolutely correct. And
And then
tail
tail.
dot prev is gonna be node. Okay, so that's fine.
Exactly.
I think
And
that's fine.
then node
Anyone have any
prev is
comment?
gonna be tail.prev.next, and then. So I guess we do need to preserve, I guess, tail.prev.
Am I the only one who's losing focus? I'm starving.
So
Okay, so
we linked
let me move faster.
we linked tail to the node, and then we linked the node before tail also to the node. That's part one. And then part two is gonna be linking the node itself to the tail and the one above it, or I guess before it. But I guess since we changed tail dot, so yeah, in next and prev is gonna be tail dot next or tail dot prev, I believe, because you're just doing the
Yeah.
same thing. Node dot prev is gonna be node dot prev.
Why am I mixing pointers? I don't like
So
pointers. Man. Okay,
yeah,
home.
Guys,
but
but
Yeah.
no
node,
dot prev it should be tail dot prev, but tail dot prev got changed. So I believe those need
So
to
let's
be
preserve
done,
tail dot prev.
or we can
Yeah.
put those
Okay.
above. We need to put those
are
the
we
nodes above the
if we
tail.
are inserting in the end in the tail, so
Exactly.
Okay, so let's do this for real this time. Okay. Okay, so first thing we need to do is preserve the tail, the tail dot previous and this nodes dot next, right?
I don't believe we need to preserve anything if we keep it this way. So first of all, you link the node itself. The next to it is going to be tail. The previous is going to be tail prev. And then you link the tail and the previous to the node itself.
Okay.
That way
There.
you don't move anything that you're still gonna use.
Oh yeah. Oh, yeah.
Okay. There it is. I think I got it. I'm not looking at the screen right now. I'm just wrote it with a pen and paper. Tail. Just like I painted the notes. Tail dot prev. Dot, what the heck? Tail dot prev dot next equals node. Okay. Node dot next equals tail. Tail dot prev.
Equals node.
Tail dot prev equals node. Node.
Yes.
Oh no. We can't do that.
Why not?
No, node dot
This is
node dot
wrong,
prev
right?
equals node dot prev equals tail dot prev. Then we
Yes.
say
Yeah.
tail dot prev equals node.
So you change the node itself and then you change the surrounding. So line 46
Okay,
is
so
gonna need to be node.prev equals tail.prev.
This
Yeah.
is the importance of pen and paper.
I think that should work. I think that should work. Without line 45, yeah.
yeah, we don't need this one. So that doesn't work.
Ah,
Okay, we're good. So node dot previous. Yeah, so if you observe, it becomes tail dot previous. Wonderful. Node dot next. This pointer. Oh, the node dot next catches this pointer. No. Yeah, true. Then tail dot previous dot next. Tail dot previous dot next comes node, and tail dot prev becomes node. So let's see how that will work out for us as we go about putting. So yeah, so now we need to remove back to where we were, square one again. To remove. So
I suggest we scroll
where
back
are
and
we?
take a look at the solution we did so far.
Hey, so we haven't done anything really related
We
to the
just
cache
initialize
so far.
it. We
We've just
Yes.
been doing housekeeping duties because this is a kind of a cumbersome process. I think they were right when they said it on Wikipedia. They said it was
That's nice, I guess.
cumbersome.
Yeah.
So the whole process, that's the only thing we've done. We're still trying to do housekeeping so that we can get to. Yeah, so now we have a node, right? And we are able to insert a node, and we are able to remove a node from a linked list. So now we can get to the meat of the matter, which is
The
to
actual
access a
logic.
node and to update a node or insert if it's not there. Okay.
Yes.
Right. So if it is, so now we can do this because now we have everything that we need. We now have, so if it is in the cache, if it is in the hash, and we're trying to put, yeah, so if it is already here, then we move it to the end, right? That makes sense, this part.
yes.
So if you're trying to get an item and it's already here, move it to be the most, what's it called? The most recently accessed. So self,
So the tail.
yeah, so self dot remove hash. What are we gonna have it? Where's it gonna be going? It's gonna be the dot hash key, right?
Yes.
That's correct. Absolutely.
Yes.
Okay.
You can store it
Yeah.
in a node and then insert it. And make a remove return the node that you removed.
We could do that. I actually had that problem. We could do that, but we need to update, right? So
Yeah.
that's the issue. So we could store it in a variable and go back and what's it called? And then re-add it, reattach it at the end. But sometimes you may have a key which is already there, but they have changed the value. So you want to change it from a 1, the value to become something else like 13. So if you store it in a variable, you're gonna have.
So how
I
do
don't
you
think you
how
have to
about you
store it
remove
in
it from the
variable.
hash map completely and then
Yeah.
just add it to the hash map as if it's a new node.
Yeah. So.
So you have it the hash map with the key. So if you first, if it's already in the hash map, you remove it from the hash map, and then you like you just add it as a new one afterward in the else, because if it's not in the hash map, you already add it. So just
believe we're almost there. So if it's exceeded, is it going to be greater than and equal to, or just greater than? So we check and then we remove. So if it is greater than or equal to, right? At this point, it might be equal to. So if it's equal to and we are going to insert, then we need to remove one. Yes, so we need to remove one. Is everyone following? Let's get to a part, because this is a lot of work. We are already 51 lines of LeetCode. That never happens. So self. Right, then we remove and we delete it from the hash. So that one is done. Is there anything else we need to do at this point? I think it looks like we're done. I don't know. Anyone see anything missing? So if update the value if the key exists. So if the key exists,
okay, you removed it. Now add value to it.
Yeah.
I mean, you removed it. Now update, or I'm missing something here.
Do we need this outside of the else statement?
In the if that one that you removed, you need to insert it again.
Oh yeah.
In the end.
Okay. That it feels repetitive, but we'll figure it out. No.
There's something wrong. Like you just either change the value or put it at the end. Or I'm not even understanding the algorithm.
So if it is in, you remove it from its position, put it at the end.
Yes.
Right?
Now it's good.
Else, if the cache is at capacity, you get the what? Oh yeah. So the node, you get the least recently accessed item, which is going to be here, which is the head.next. Then you delete its value from the cache and you remove it from the linked list. So let's put those ones together. And now we're good, right?
Yeah, I think so.
And we create the new one, the cache, and we insert. Everyone happy?
But why you remove the head next? You should remove the head.
No. The head is simply there for us to access like this. The least recently is this one, head.next.
So okay. So I understand now. No, that node is the head in an actual map. In the house.
Yeah, it's just.
Yeah. Okay. So
yeah. That was the bone of contention. Yeah, it doesn't do anything. Its only purpose in life is to allow us to do this in this line. Yeah, and we haven't even used it anywhere else. Okay, so everyone is happy. I think this one might work. We'll see. Now we can do this one. So get, where is the question again? Get operation. What is the process for get? Return the value of the key if it exists, otherwise -1. That's simple enough. We're almost home. Stay bear with us. So first thing, return -1. It's the default. Okay. Otherwise, you need to check. So if the key is already in the hash map, so it is already here. So that's going to be if key in self dot hash. Then what is supposed to do?
I think there's a problem because I think The hash doesn't accept numbers like the object, the text in Python.
It does not?
Yeah, it doesn't accept numbers as keys. It only accepts strings.
I think it does.
No. For JavaScript, it doesn't. I don't know about Python, but I think it's not. It
I
doesn't.
think
It's
Python
only,
allows you to.
you can use map.
Let's see what will happen.
I just
Jump
checked.
again.
It does actually. It does accept. I just checked.
It does, okay.
We could have checked. But thank you for confirming, Sabah. Thank you very much. So what do we do? So we return says return the value. The value is
No,
in the
but before you return it, you need to add whatever you will add, as that would be like the least, the recent, like the recent, the most recent used.
Oh yeah,
right?
exactly. Thank you. Yeah, see, you're awake. Very nice, very nice. Thank you.
Yep.
Thank you. So we don't just return. We have to also do our homework to
Dot
self
val.
dot.
Dot val. Dot val.
Sorry. Right. Thank
Yeah.
you. Man, I
Yeah.
went to sleep, but it's fine.
Oh
Dot remove.
man, that was 3 hours.
Okay, so let's
Oh,
just finish this self done. Man, I think I'm falling asleep. Key. What happened? We do the same thing.
dude. No. Yes.
That's valid.
No, I think so. As
Hey,
far as my brain
that is not
capacity.
time for the drama. Everyone, cross your fingers. Hold on to your chest. Hold on to your pals. We're gonna run this. Wow. Okay, so let's.
Bismillah. Come on.
We can try zoom out. Hold on.
Yes. Where's the submit button?
Where's the submit? No, sorry. Is it? No. Hold on.
Where is
Where's the
it?
submit? Anyone know what's it?
It was at the top, but where is it?
Scrolling up from the scroll bar, I think.
Oh yeah, the page
Is it
itself,
this
not the
one?
code. Yeah, there it is.
Oh, come
But I
on,
was zooming
PacMan.
out. I was zooming out and nothing was happening. It's shrinking the text
Okay,
instead.
PacMan,
It
just
was
run it. Just
editing.
run it.
Okay, everyone, hold on to your pearls. Okay,
Haydi.
and where is the thing?
Self detach. Now hang on, in the insert, are you sure that you should have been using self.tail, right? Or I'm missing something?
He's telling us the
Oh yeah,
problem is node key. Runtime error is
Val is not
not
defined.
defined.
Check your data structure.
so
Check your linked list.
value.
Is it value? Okay. Go up. Yeah,
Is
value.
that value?
Yeah,
Yeah.
and the keys as well. And
Yeah,
the
you
keys
have
Loy
it
between.
is
valid.
right.
Got that.
And Loy is right.
And the
You need to be using
Okay.
self.tail, not just
self.tail. Yeah, and the last two lines. The last two lines. Yes. Okay, this one as well.
Mhm.
Yes,
even
sir.
all 4 lines. Even
Oh,
all
45, 54. 54.
Uh,
The
oh,
54, there
sorry.
is there.
Yes.
Okay,
On the
sorry.
top? No,
Sorry.
you know, still on the top. On the top. Like, go, scroll up.
What happened?
Scroll up. There's something, there's
What?
another value as well. Scroll up. Yo, up, not down. Yes. It stops. Yes, there it is.
Just make sure.
Oh.
Hmm.
Slow down. We tackle it one error at a time. No problem.
Wow.
Okay.
Errors. It worked for one.
We got one case right. So why?
Let's see.
What are we doing wrong?
So for this one, it returned 5 instead of a 2. So we inserted so this is the size, then get 2 null, insert 2 null, retrieve 1 not there, retrieve 1 not there, retrieve so this is put, so put 1 and 5, put 1 fine, and then update. So the update is not working. So
yes,
this is supposed to update is not working. Update is we are doing this together. Don't blame yourself or anything. Okay, so
this is a group effort. This is a group problem.
Yes, it is.
Okay, so if it is inside, you remove it, right?
I just remembered, where's Monsif?
Monsif is apparently still sick.
So sick?
Still sick?
Like, I've
No,
been, like,
still.
He's, like, how is he, like, is it something to make him, like, be absent all the time?
You can message him. I don't know.
I mean, when I message him, he just doesn't respond or something, or even, like,
And
really...
he must be sick enough not to respond. I don't know.
He was not sick enough to have fun activity on Twitter and LinkedIn yesterday. And yes, we are officially stalking him to make sure he's okay.
You're officially what?
Stalking him to make sure he's okay because he's not been responding. So we are officially putting an alert on him to make sure he is okay. He's alive.
Remote? I don't think this is gonna work this way. Well, it.
Okay. Okay. You are using else. There is no need for else actually.
We need this to happen either way, right?
Okay. You know what? Can you do
For a
something?
new node.
Can you do something? Remove the insert and else and push everything out, the indentation out. So the only between the key, if a key in it, you just remove the key. So what I'm saying is line 37, line 38, comment them out. Don't remove them, comment them.
Okay.
And line 30, no. Where 36?
Not done.
37, leave 37. 38. Leave 30. Comment 38 and leave 37.
Okay.
And comment the L. 39. Comments 39. And everything else, just take it out of the else statement. Just yeah. Yeah. Okay. Now let's check at it. I don't know yet. But let's just.
Oh, passed for one more. So the update is the part that is not working.
Yeah.
So if it is
it out
in,
now.
so we need it is already in. We need to remove it.
Okay.
And set it as a new value.
Can you do something? Can you do the lines 47 and 46 above the if len, above the check of the len statement of the check of the lens? So line 47, 46 and 47 made them after 39. Yes.
Wait,
yes,
so
okay.
You add before checking if you should add?
Yeah. Then you check if it's bigger than, remove the equals.
Okay.
So if you exceeded the capacity, what are you doing then? You have.
Pardon, I can't hear you. Lost you for a moment.
And then remove, and then that. Okay.
Yeah, but you should put them in
don't remove the node. Remove the head. You have the head, yes?
Guys,
you have the node equal the head. So yeah, I guess it is.
Look, Victor, just put the code in full screen. Put the code in full
Yes.
screen and let us zoom out and let's like go line by line and see what's happening.
Oh,
All
Minna
right.
Oh, it's
fixed it.
fast. Minna is not asleep. She's awake.
Yeah, sorry, I made a mistake. I should not have said you're asleep. You're wide awake, I see. Okay, so in this case, we're just brute forcing. By any put is going to insert either way. Only time, and then we just check if we have exceeded the capacity, right?
Yes.
Okay, wonderful.
Very
So, do you want to see who will pass?
good job. Very good job.
This was a team effort. Took the longest time ever.
And it
We
deserves
don't know if it will pass yet.
another one.
That one was for you. Okay. Let's see what happens.
Okay. That was
Congratulations.
actually that is
Did
the
you have
reason
a-
I hate this type of problems.
Okay.
Did you have a previous time where you sat more than 3 hours straight?
Oh,
We've had a
okay, you're
few.
kidding. By now I would have been fully asleep and you would have told me a bedtime story by now. Ask Sabah about it. That
Yeah.
is basically if you're not now.
Look, I'll tell you, like next time that could be improved a lot. Look. Let us first, okay, without even having to know the problem beforehand, but let us take some minutes, okay? Not for
No,
today, don't worry.
Sabah will send the problem next. Like
Yeah.
we'll post it in the channel for everyone to prepare about it, and yeah, we'll take it from there so everyone have at least some idea about what's going on.
Yeah.
And I think it was a group effort. It was a very nice group effort.
I think so. And within the time that we are solving the problem. Every now and then, we don't jump to the code directly. We do pseudocode in the middle. So we did the flow chart. We really
We did a
understood,
lot of
visualized
we
it.
do a lot of pseudocode beforehand. Like Sabah did pseudocode and
Yeah, I mean, this
Victor did
particular one.
pseudocode. I'm the only one who jumped straight to the code, not not do pseudocode.
Yeah,
I think
because
I think we were pressed with time. That's why we didn't.
I think something happened today. I don't know. It's
no, I'm
Indeed,
not
because a
judging
lot of
anything.
technical
Just
difficulty, Discord
and
was
this
really
problem
fighting us
just
today.
I don't know.
yeah, and
Discord
I
was
highly guys,
really
I
fighting us.
really do not want this effort to get lost. So please, if you can, not you can, you have to you set the time for it today, or even sleep over it, and or even just take a sneak peek on the solution one more time. And tomorrow, please, if you will not solve it by yourself again, go just take a look at it like line by line, okay? Because otherwise, these neurons will just disappear.
PacMan,
Yes.
Rihsan is telling you to put the code in the chat.
Yes.
Sorry.
Lahsan. Am I correct this time?
Oh, sorry, Lassen. Let me get that for you.
What is that?
Okay. I was not paying attention.
His name Luai. His name Luai. Am I correct, or did I butcher it this time again?
After all that work that we have done, we can look at. Can we look at one more solution using? We factor the code a little bit.
I would love to, but no, please. Let me.
Just a moment. I just want to show you something a bit ridiculous about Python. I know people.
Okay.
Please.
So what we can do here is let's just import to be explicit. Collection or is it collections or collection?
Collections, I guess.
Yeah, collections.
Does it have S? I think it has S.
Yeah.
And in LeetCode, you don't need to import it. You just use
I just
what
wanna.
you're gonna import. You don't need to say from
I
what.
wanna.
In LeetCode, you don't
Make
need
sure
to do that.
it's all the code that you need. Sorry, it's all the code that you need. We can remove that and remove the pointer back. Then we can look at init. So instead of we have the capacity, we have the hash. Instead of having a regular hash is going to be this ordered dict. And then so initialize. We don't need the pointers. We don't need the pointers.
So you're not doing it. You're using a status structure, not.
Yeah, we're using this built-in.
We were
from
like
Python.
imitating C, like we're using Python and ignoring the Pythonic way. We're just imitating.
Yeah, this
C,
is the Pythonic way.
Oh,
So I guess we'd call it the
yeah,
Pythonic way.
Okay.
like Python
So
has its
proceed.
implementations here. Okay, let us see. Oh, okay, okay. I thought you would use another
So
algorithm or something, so I wanted like to make my head around this first. Because I don't want to like, okay, we solved the problem, but next day we didn't really get the idea, or we didn't like build a thought process. That was my problem.
yeah, so I just wanted. Yeah, so it's actually better if we do it this way because now we know what's happening underneath.
Show the code.
I'm almost. I think it's there's a small.
I think it's when you move it to the end because there's both. Oh, okay. So
You remove it.
you put it in the end.
Delete it, not remove it.
Because you move it to the end, you move it to the end, and you or will it be replaced?
If I move it to the end, it was supposed to do the delete and insert using this.
No, last line. This one will
The
move
last
it to the end. Will the last line replace it or not? Or it will add another one? If it will add
yeah.
another one, then there is a problem.
Is the problem here?
If it will add another one, if it will replace it, I think I don't think.
You're saying so if it is in the hash already, then you just move it to the end.
And
Yeah,
then
but
update the
the
value.
last line will add it if
It will not add it, it will update the value since the key already exists.
okay.
So what's this? So this one is this one is okay. So 2, 1, 2, 4. Get one what? No, this is get 1, get 2. So get 2 did not update again. What is this happening? Mana, are you sleep?
2 got inserted at the beginning, so it was supposed to be there, and got updated later on, and then
I think
it's
you need
not
to move
there.
the else. I think you need to move the else.
Doctor, can you send the documentation because I don't actually know how order take to work, so I just need to
Sorry.
send the documentation. Yeah.
The
Can you
lecture is
just
ordered list,
remove the
the
else?
ordered text.
Actually, I was just trying to read it. So yeah, official docs in C Python. Okay, I think we can end there because it's getting really late. I'll just send the code in the chat. So by the time the recording comes out, it'll be ready, right?
Can you send the version that you have now?
Can you try it with the removing the else?
Okay. But I can't remove the else because I need to.
You can remove the else and indent whatever comes next. Or is it just that?
Could be the pop item. It might be popping from the wrong side.
Yeah, but that would
Pop
pop
item
the
is supposed
item.
to.
It would pop the item even if, like, we already have it. It will pop an extra item. I don't think that's correct.
We have a method for. Okay, so. We've seen the. I've sent to the. So, capacity. We give it the dict. It is to the end, return key. Unless you didn't find it, so that's fine. So the put is the issue. It is in. Let me check something. Yeah. So default is the last. So let's see. That should be true. Oh, that should be the opposite. Bring back the. So now it's doing the opposite. It's true.
Do you know why I ask you to remove the else? Because let's suppose that it's not there, but the len is more than the capacity. It will add it.
So this should be that.
No, let's suppose the len is more than capacity.
Yeah, so that's what the else is only. That's the only thing we need. If we have exceeded the size, then or we are
But
equal to the size of the capacity, then we just remove one item and we move on with the life. Otherwise, we can insert because we may have like 5
yeah,
items and we only have 2 so far.
Yeah, I understand.
Okay. So I think this was the problem. So this implementation by default will remove first in, first out. So it was removing the most recently accessed instead of the least recently accessed. So last in, first out. Yeah, so first in, first out order for still there.
Yeah, yeah. So pop item on itself, what does it pop without the last false? It pops the last?
That's what we can retrieve it. So if we want to see it, we can just if we just have printed it from there. Okay, so now we what's the steps? So when we put we put 1, we put 2, and then we get 1. So 1 should be at the big, should be the most recently used. So now the item to remove should be 2, right? So if get and put are working correctly and this move to end is actually doing what it's supposed to do, our list should now have basically 2, 2 followed by 2, 2 followed by 1, 1. So now when we do this pop item by default without anything, it's going to remove this one, right? So if we do that,
Need to remove that last list.
Documented. Sorry, commented.
so yeah, so now it's removing 1.
I
See?
Alright. Okay.
So now we need to specify, as they say here, they say that if you don't specify this last to be false, so we just take that, put it here, and we say false, as they say in the documentation, which we were told and we did not read. it should now pop the correct item, which is the least recently used, which is
Makes sense
is it the last?
because we are removing from the beginning, and the pop removes
Yeah,
from
yeah, we need to
the
remove from the beginning.
end. Yeah.
Yeah, yeah.
We're finally
I
done.
believe we're done. Finally, after the record time of this was 3 hours.
Actually,
30
this
hours,
one
3 hours 30.
is yeah.
Guys, I